Hello, everyone. Welcome to the weekly colloquium series of the C3.ai Digital Transformation Institute. So we are a consortium of universities and industries dedicated to the use of artificial intelligence, machine learning, and cloud computing to affect digital transformation in society. So the Institute is headquartered jointly at Berkeley and Illinois, and our university partners are Carnegie Mellon University, KTH, MIT, Princeton, Stanford, and the University of Chicago. High performance computing support for us is provided by the Berkeley Lab and the National Center for Supercomputing Applications. The Institute was started with a generous donation from C3.ai and cloud computing support from Microsoft. And other industry partners include AstraZeneca, Baker Hughes, and Shell. So in addition to the colloquium is part of a series, and we'll continue to have other talks this semester. So the next talk is by Murat Arçak at Berkeley, followed by John Doyle at Caltech. Sanjay Shakotai at the University of Texas in Austin will speak after that. Wei Liu from KTH and Kaiyu Guan from the University of Illinois at Urbana-Champaign. We also have a workshop that I encourage all of you to attend. It's about the digital transformation of the built environment. For those of you who don't know what the built environment means, this basically means something like smart homes and smart buildings and smart offices and so on, and how AI, machine learning, and cloud computing can be used to design and build such environments. So this workshop will be held on October 26th and 28th, of course, online. And if you go to the Institute's website, you'll see more details as to the exact times in the schedule. And in case you missed any of our workshops or talks or symposia or anything like that, all of our events are archived on YouTube. So if you go to the C3.ai Digital Transformation Institute's page on YouTube, you can see all of the talks and you can watch them at your leisure, or if you want to watch it again, you can watch it there. Before I introduce today's seminar speaker, I want to mention the talk will be about 45 minutes with question and answer. Instead of a question and answer at the end, our speaker today mentioned that there are two parts to his talk. First, a general introduction, and then more technical details. So he will pause after the first part of the talk. And if you have any questions at that time, please post them in the Q&A box, and I will ask them. And if you want to upvote a question, please do so, and we'll try to answer as many of the questions as possible. Today's talk is titled Challenges and Opportunities in Cloud Operations Research. And we have a very distinguished speaker, Ishai Menache. Ishai received his PhD in electrical engineering from Technion in Israel. He was a postdoctoral associate at the Laboratory for Information and Decision Systems at MIT. And during that time, I had the opportunity to collaborate with Ishai, and we had a very nice collaboration. Since his postdoctoral position, he has been at Microsoft Research from 2011, where he is the founding manager of the Cloud Operations Research Group, also called the Core Group. His research focuses on developing large-scale optimization frameworks for cloud systems and applications, and his research interests include systems and networking, optimization, and machine learning. Ishai, take it away.
All right, can everyone see me? Yeah, Shrikant,
yes,
everything's
yes.
okay? Yeah, okay, so thanks a lot for inviting me. It's a real honor to be able to speak here. And, I should say, Shrikant, as you mentioned, I think one of my first visits during my postdoc period was in Illinois, and was a great inspiration for me to work with you and colleagues. And, I look forward to getting back there soon sometime. So thank you. Yeah, so as Shrikant mentioned, the title of my talk is Challenges and Opportunities in Cloud Operation Research. And let's see how it works. Okay, so cloud computing has grown immensely over the last decade. I guess all of you know that. One of the main reasons for its success is the flexibility that it offers to the users. Users, which include companies, startups, do not need to incur large expenses to purchase their own computing power. Instead, they can easily request compute resources based on their needs at this time, at the time, and scale in, scale out flexibly. So that's kind of, I guess we all know, and we all see that it's a growing market. And of course, companies like Microsoft, Amazon, Google, and others are deeply involved in this space.
By the way, Ishai, are you sharing a screen? Because we're not seeing anything.
Oh, bummer. Wait, hold on. I should share my screen, right? Yeah. So it was automatic. Where is the share? Ah, okay. Share screen and share. What do you guys see now?
Yeah, we can see it, but it's not in presentation mode. If you want to put it in presentation mode.
Hold on. Sorry about that.
Yep. Now it's great. So we see the overview slide. Yes.
Okay, perfect. And if I flip slides, you see?
Yes. Yes.
All right. So, you know, cloud providers operate at large data centers, and users can rent virtual machines or VMs for short on demand. There are other kind of scenarios for cloud computing, but our main discussion in this talk would be around the, the process of renting VMs, at least the technical part of the talk. All right. So, before I jump into, an overview of the area and things that we do, I'd like to, as Shrikant mentioned, to describe a little bit what my group does. So my group was formed like a couple of years ago. We call ourselves Cloud Operation Research. These are the other members of the group. And I should say proudly that we have two new hires that they're working from remotely from Latin America, Hugo and Patricia. That's our team. And essentially we work at the intersection of cloud, algorithms, and optimization. And in particular, that covers roughly two areas. One is cloud systems, which is all sorts of resource management problems that arise in cloud settings. And I'll deep dive into that today. And the other area of active work is cloud applications. So, maybe only one slide about what I mean by cloud applications. So in essence, we can think of optimization being used as some sort of a service to facilitate all sorts of business processes. For example, managing technicians at scale. Think of a company like Comcast that needs to assign thousands of technicians to thousands of repairs of work orders per day, or even more than that. Another example is retail, where we have to assign orders to warehouses. Where do orders are being fulfilled from? All these kind of problems require like large-scale optimization under the hood, and my team has been involved in some of these efforts. And in particular, we built some optimization solutions that are running today in productions in some of these applications. So I won't go into details, but essentially, there are really interesting optimization problems here. For example, in the area of transportation, all sorts of traveling salesman problems that arise in these settings. So again, this is a fascinating space, especially given the scale and the huge amounts of data that we have in these kinds of applications. But as I mentioned, our focus today will be more on the resource management, and more generally, I should say that we can look at the resource allocation problem as a whole as some sort of a supply chain problem, in which, and here we see kind of a schematic view of the different stages of that supply chain. So it's all about bringing compute to the end users. So that requires a lot of preparation and a lot of, assignment, a lot of kind of processes under the hood, starting with demand, forecasting demand for the future, seeing, some projections of demand, and based on that planning. What do we mean by planning? When do we buy servers? At what capacity do we buy servers? When do we build data centers? Where do we build data centers? All sorts of these questions have to be answered. And of course, it has a huge impact on the business. If you don't build on time, you may lose some, some customers and so forth. So there is a planning phase followed by sourcing. Sourcing is, of course, the process of, buying equipment. If we want to generalize that, is also, all the process of, building the infrastructure itself and all that, buying the right equipment and so forth. And then after we have all this procurement done, there is an execution phase in which we have to place all this infrastructure. We have to place it in data centers, right? So we have to take the servers from warehouses and ship them to the different data centers. And I'll touch a little bit more on that part, on the execution part. Once the servers are in the data center, of course, we have an important aspect of capacity management. How do we manage those servers? And that would be probably the focus of this talk. We'll talk about the VM allocation problem, which is key, which is a central component in capacity management, which occurs at a very fast time scale of we have VM requests that arrive and we need to assign them into physical machines. So how do we capacity management is how do we manage the server capacity that we have in a data center in an efficient way that accommodates the needs of our customers. There are other processes that are relevant after the execution phase. One of them is decommissioning. We all know that servers have a certain lifetime, so it's an interesting problem of when do we decommission servers and where. And this is also a very key component because we, of course, the amount of space is limited, and we want to replace old hardware by new hardware, but we want to do it in a very thoughtful way and in a way that has a good return on investment. So these are kind of the parts of the cloud supply chain. As I mentioned, I want to zoom in for a little bit on the execution phase, which is one active project in the team. And in particular, the execution means, as I mentioned, so we purchase, let's say that we purchase servers and we store them in the warehouses. And then when we have some customer demand, so demand could be, for example, an internal demand for, like, you know, in the Microsoft context could be demand that comes from Microsoft Teams or Microsoft Azure or Office 365, right? When we have these projections of demand, we have to decide which suppliers do we use to fulfill this demand. How long do we store the existing servers in the data center? We have to be aware of depreciation. And then we ask ourselves, once we see this demand, how do we ship it to the data centers? Maybe they are different forms of shipment. Would the servers arrive on time? And what is the associated cost with this shipment and other factors? In the data centers themselves, there are a few interesting optimization problems. For example, we have to prepare the infrastructure ahead of time. We cannot just ship the servers and assume that, you know, after they're shipped, they will be kind of ready to go. We have to prepare cables, networking, and all that. So that's a process that takes around in the order of weeks. And once we do the placement itself, we have to account for space, power, cooling, and decide where to place the servers themselves. It's some sort of a bin packing problem. And it's quite challenging, especially the power dimensions. We want to make sure that we want to make sure that we don't strand power, that we use power efficiently, because that has huge impact on our COGS. And of course, we have to also be aware that we cannot ship 1 million servers per day. The data center facility itself has some throughput that has to be accounted for. So all these considerations can be casted as a large optimization problem. And you know, that's something that we do in our group. And I'll just mention in a nutshell the challenges that are associated with this kind of research. First of all, the scale here is huge. We are talking about, you know, potentially hundreds of data centers. The demands themselves could be a large number of demands, and the options within each data center, there are many different options to place an existing demand. An interesting aspect here is the stochasticity, the inherent stochasticity of the problem. The demands themselves are a projection. They're not exact demands. So we have to make some projections that could be inaccurate. How can we account for this inaccuracy in a systematic way and still kind of be okay and don't incur any losses? So that's something that is kind of, for those of you with more theoretical background, can think of these kind of problems as stochastic optimization problems, where the input is stochastic and we still have to embrace this stochasticity and make decisions that are kind of robust and account for different you know, scenarios and different realization of the stochastic elements of the problem. As I mentioned, another problem here, another aspect is the fragmentation that we can incur. You know, if we place in a way that is not efficient, then we may be wasting power, maybe wasting space. So we have several dimensions that we have to account for when we do the placement itself. All right, so I'll pause here for a second because then I want to dive more into the technical part of the talk. So I want to welcome any questions that you guys may have. I cannot see you, so it's a little bit, I guess, Shrikant, are you
Yeah,
moderating?
if you have questions, please post it in Q&A and I'll ask Ishai. I have a quick question, Ishai.
Yeah.
I know the second part of the talk is on online allocation. I was curious in the sort of the portfolio of problems that your group looks at, are most problems online problems, or are there a lot of problems that are sort of offline optimization problems that are just large?
Yeah, you know, that's an excellent question. Let me return to this slide about the cloud supply chain. So first of all, let's talk about timescales, because that can give some indication to answer partially what you're asking. So I would say, you know, for example, when we are planning placement of servers, we can think of timescales in the order of like, you know, days and weeks, right? So in that case, I guess every optimization problem in our space is some sort of online optimization problem, because you're doing something and then something else will happen in the future that you don't know. So all problems are online in principle. However, because the timescales here are kind of, you know, we have a lot of time, then oftentimes we can treat some of these problems as offline and we'll still be in a good shape. Right, intuitively, if we have very large time scale, we can essentially solve, let's say, an integer linear problem. We have enough time, we can treat that as some sort of an offline problem, and we will be fine. In the VM allocation, where the time is kind of the response times is in the order of milliseconds, then I think it's a more like a pure online optimization problem, if it makes sense.
Yeah, thank you.
Okay, any other questions before I dive into more like math and algorithms?
There seems to be one more question.
Sure.
From John Gokson. How do you weigh demand forecasts as time horizon increases? I don't know if you can see the question.
Yeah, I'm not sure I understand. How do I weigh? Maybe.
I guess maybe if the horizon that you're looking at is large, maybe it won't be as clear. I'm not sure. So maybe the John Cookson, maybe you can clarify. If you want to put more details in your question, we can come back to it at the end.
Yeah, I would say, you know, at least we are looking at again, we are making a simplification when we solve these optimization problems. We are looking at the supply chain case. We're looking at for let's say in the order of like 1 month or 2 months ahead. Although we know that we're going to have demands that will come in 1 year, but realistically, it's good to optimize for you know, a month or two, with the understanding that we can re-optimize. So that's something that we do. So we solve for let's say the next 6 weeks. However, you know, we can solve again let's say in the next day, and account for new things that we encounter. Similarly, I think I understand Maury's question now, is that, you know, things that happen far into the future, we can pay less attention to. We can put some discount factors. I think that's kind of the question, that will account for the fact that, you know, we don't really care about what happens in 6 weeks ahead of time, because we know that we can fix it, let's say next day or in a week. So we do have this kind of idea of discounting when things happen far into the future. I think that was the intent of the question.
I think there is also a question from Varun Gupta. It says,
hi Varun.
Yeah, on-demand stochasticity. I imagine creating the scenarios or the distribution to use for stochastic optimization themselves are subjective. Can you say how you think about this, historical data or just marketing forecast? Yeah, I guess, how do you build the distributions for stochastic optimization?
Excellent question. I think that you know, we try to we have the data, so that's one advantage that we have, and we can look into the data, and we do have data science teams that can analyze this data and perhaps, you know, build some distributions around this data if we need if we do need some distribution form for our algorithm. So yeah, we do rely on data and try to kind of create models based on this data. So that's an important component in all of what we do. And I think I'll touch upon that also at the end. How do we one of the challenges is how do we infer interesting things from data and incorporate them directly into our algorithms. So definitely we look at data and we either build models or do other things with this data. For example, train some models that will help us later with the optimization, but that's some other kind of research that I won't discuss today.
Thank you.
All right, so let's move on, I guess. All right, so again, the technical part of this talk is about online virtual machine allocation with lifetime and load predictions. This is joint work with Konstantina from my team, from Yaron, who was a former intern from the Technion, Niv from Tel Aviv University, and Sefi from the Technion. And again, the context here is that we are looking at the capacity management. We are zooming in into capacity management where decisions have to be take place quite quickly. So let's dive into the setup for our problems. Cloud providers have many physical machines in the data center. When VM requests from users arrive, they place the VMs on physical servers that have enough capacity to serve them. Efficient allocation decisions are crucial in this setting. Inefficiency leads to fragmentation and the need for more machines or higher power usage. Our goal in this work is to design algorithms for allocating VMs to physical machines so that the total time the machines are used is minimized. The problem has some similarities with the dynamic bin packing problem that you may be aware of. We can think of the VMs as items that arrive and depart over time, and we need to pack them in bins, which are our machines. However, we do not minimize the number of bins as classic bin packing problems, but rather the total duration for which we use them. All right, so we minimize the total duration in which machines are being used. Why do we do that? Because that's a good proxy. If we can minimize the total duration in which machines are used, it's a good proxy for using less machines later on, or providing or over providing the data center, and that has an immediate effect on COGS. Also, keeping machines idles is good for power and other considerations. Before I move on, I should point out that my group is deeply involved also in the VM allocation problem, also from a practical perspective. So the work that I present here is more theoretical, but we actually work directly with Azure on more practical aspects. We essentially try to take our theoretical ideas and implement them in practice. And I'll discuss this towards the end. How do we bridge the gaps between theory and practice? For more on the system itself, on the VM allocator, we have an OSDI paper that you can look in more details. No equations, just the system itself. From now on, we will refer to VMs also as intervals, as kind of common in the literature. So each interval I has a length of Li, which is each duration. So length and duration, I will use it interchangeably. And the width or size of Wi, you can think of it as the CPU that VM requires. All sizes are between 0 and 1. We will discuss two settings in terms of the width. In the first, all VMs or intervals have the exact same width. So that's the uniform case, which essentially that would be the focus of my talk. In the second, the widths are general. They can be arbitrary between 0 and 1. Regarding the physical machines, we will refer to them simply as machines. We assume that the width size of each machine, we normalize it to 1. And we say that the machine is open or active when it has at least one VM or interval running on it. Okay, so our goal can be expressed as follows. How can we pack the intervals to the available machines so as to minimize the total time that the machines remain active? We assume that we have enough machines to schedule all VMs requests, so that rejections are not, we don't need to reject any of the VMs. So no rejections in our setup. We have enough capacity. Any questions about the model? Actually, I want to see if the model is clear before I move on. If there are any quick questions about the model itself, about the objective, and so forth. Shrikant, any quick question?
So is this a fixed horizon problem, or do things arrive and depart forever, or so
yeah,
when you
it's
say
an online problem, but we assume that the horizon is kind of capital T. Okay, so yeah.
Okay. So you within the capital T
It's for the analysis mostly, but of course the algorithms do not use this capital T. It's more like something that we need for the analysis.
There are two questions. One from Varun, which says, in practice, does LI depend on other jobs on the machine?
On other jobs, no. So the VM request, think of it as, you know, you deploy a VM, and essentially you want to run it for a certain period of time.
I guess maybe the question is, what if you have parallel jobs? So you might request 2 VMs or 3
You
VMs?
might request, yeah, you might request 2 VMs. They will be broken into 2 VM requests, and but you know, there are no rejections, so essentially the system will satisfy both of them. We are not dealing here with sometimes there is some kind of location constraints, like the 2 VMs have to be in the same zone or the same data centers. We don't deal with that here. But of course, in practice, that's again one difference between theory and practice. In practice, we have all sorts of other constraints that have to be taken into account, combinatorial constraints and others.
Another question is, what is the width? Can you define it again?
Yeah, the width is the size of the VM. So, you know, a VM could be 1 core, could be 2 cores, 4 cores, etc. So, but we normalize the server capacity to 1. So in that case, you know, if the server has like, I don't know, 20 cores, then getting a one core machine, 1 core VM would be 1 over 20, a requirement of 1 over 20. Great. In the uniform case, we assume that actually captures most of the algorithmic insights and techniques. We assume that the all VM sizes are the same. And again, in practice, we have, I should say that we have multiple dimensions. We have CPU, memory, and others. In this talk and in the paper itself, we simplify to 1 dimension only. So if you're interested in extensions, one kind of important extension is the multi-dimensional case. All right, thanks for the great questions. Okay, one important notion is that of the load vector V, which is the histogram of the VM capacity that is required over time. So at each time t, the value Vt is given by the sum of sizes of the intervals that are active. This gives us the minimum number of machines required at that time. For example, if at time t we have 3 active VMs of size 0.5 each, we know that we need capacity of at least 1.5, which means at least 2 machines. Okay, because we need to round it up to 2 machines. So the load vector also leads to a straightforward lower bound for the problem. Okay, it's essentially the L1 norm of Vt.
One other question which is, do we have to serve VMs immediately, or can they
Great question. Yes, the answer is yes. So unlike job scheduling, in which you can sustain some latencies, here you have to serve the VM immediately. Thank you. In the online setting, that is the focus of this talk, VM requests arrive over time. The precise arrival time of each VM is not known ahead of time. When a VM arrives, its width and size is revealed to the scheduler. The VM's lifetime also, or the duration, also becomes known upon its arrival. To evaluate the performance of online algorithms, we use the common notion of competitive ratio. We say that the competitive ratio of an algorithm is alpha if the online algorithm pays at most alpha times the cost compared to the offline. For example, competitive ratio of 2 means that the online algorithm pays at most double the cost. The best result in our setting is by Azar and Weinstein. They show an O square root of log mu competitive ratio and show that this is optimal. Here, mu is the ratio between the longest and the shortest interval length or duration. This result uses the values of the VM's lifetimes, which can be obtained in practice via ML systems. So in our talk, we will assume that the VM lifetimes are kind of, once the VM arrives, we know the exact lifetime of the VM. You know, in practice, this is of course not exactly the case. We can estimate the lifetime of the VM, but let's assume that we know it perfectly. you know, to obtain the results that we need. So and actually we can estimate the VM lifetime in some form of accuracy. So how do we differentiate from the model of Azar and Weinstein? In this work, we explore how we can use additional information on top of the VM lifetimes. This is motivated in practice by having, nowadays we have machine learning systems that can provide increasingly richer predictions of quantities of interest. In fact, Microsoft itself has a system called Resource Central, which produces such predictions for the compute, our compute infrastructure. In particular, we look at two sources of additional information besides the VM lifetime: the future load vector and the average load. The future load vector is the histogram of the upcoming demand. Since that is an aggregate over all VM requests at any time, it can be predicted with quite good accuracy. In that case, when we do the kind of time series of the aggregate future demand, we can show, as we can see in this table, we can show a two competitive ratio, so a constant competitive ratio for the uniform case. And that will be the main focus of our talk. I will describe how we do that. The average load is a single number, so that's even easier to predict. It's the total load divided, the total load in the system divided over time, divided by the length of the time horizon. It turns out that just this value, which can be estimated with very high accuracy, again, because, you know, it's just a scalar, in fact, can improve significantly the performance of the scheduler. A different way to express this result for when we know the average load is that we pay the optimal cost opt, okay, plus an average additive term of square root v average times log of mu at each time t. That's for the uniform case. So again, this is an improvement over Azar and Weinstein, and we get rid of the multiplicative factor when we don't have these demand estimates. But again, for the when we know the load vector, actually it's a big improvement because we get a constant competitive ratio. So for the remaining of the talk, I will give an overview of the two algorithms for each of the cases when we know the load vector and we know the average load. And actually, I'll focus more when we know the entire load vector. Okay, so essentially, so again, let's assume that we know the load vector, we know the aggregate load into the future. The algorithm that we will design will be based on an idea of covering. What do we mean by covering? Considering, for example, we have kind of an illustration where intervals arrive over time. Okay, so the left number corresponds to the arrival time, and the right number corresponds to the departure time. Okay, so it's a uniform case. We can see that all the widths are the same, and in this case, they are equal to 0.5, which means that at most 2 can fit on a machine at each time. A cover is a set of intervals that cover the time horizon with load between a minimum and maximum value that is specified as part of the cover definition. For example, these two blue intervals cover the horizon, since for t equals 0 to 19, the whole horizon, in fact, there is at least one active interval in the cover. For the min and max value, let's show an example with a 1-2 cover. So the 4 intervals, the blue intervals, form a 1-2 cover, since the load everywhere is between 1 and 2. Okay, let's look at a couple of time steps. So we have a load of 1, we have a load of 1.5, with the only exception that we allow to drop below 1 when the total load in the system is not 1. So we cannot get a load of 1, and we see this in the that we get 0.5, but the total load is 0.5, so that's fine. So these 4 intervals form a 1-2 cover. Okay, so we use that notion of cover as a building block for our algorithms. Now, why are covers useful? A cover can easily be scheduled on machines. In the uniform case that we just show, a 1-2 cover, right, at any point has a load of at most 2. So 2 machines that are open for the whole time horizon are sufficient to schedule all intervals in the cover. At the same time, each cover has load everywhere of at least one, with the exception that I mentioned. So for each time, we are using at most 2 machines to schedule at least 1 unit of load. So that's quite good kind of efficiency. And that's kind of, you can think a little bit the intuition why we get this factor of 2. Hold on, my light went off. That happens. I hope it goes back on. Hold on. I think I have to move and show. Sorry about that. Yeah. Yeah, so it turns out that in the offline case, when we know all intervals, we can construct quite easily and iteratively. We have a process to construct this 1-2 covers, which lead to a two approximation algorithm for the offline case, assuming that we know all intervals. So this process kind of relies on knowing where the intervals are, picking a point in time in which we have a high load and removing one of the intervals and keep going like that iteratively until we reach a 1-2 cover. But that process requires knowing where the intervals are, and it's also intervals that will arrive in the future, which is of course an information that we don't have in the online case. So we have to essentially rethink how do we use covers in the online case where we don't know the exact intervals that will show in the future. We don't know their length, and we don't know how many intervals will arrive and so forth. All we know, I emphasize, is just the total load into the future. All right. So as I said, in the online case, the things are inherently more complicated because we don't have the information on which intervals will arrive in the future. The online covering algorithm, which we'll present next, creates a set of covers in an online fashion. The algorithm consists of 2 components: a method to create single covers, where upon each interval arrival, it decides whether to accept the interval and make it part of the cover or reject it. Then we have a main algorithm to create multiple covers. It runs multiple copies of the single cover method, which generate a set of covers. Each cover can then be easily scheduled on machines like we described before, the same principle that we described before. So at the beginning of execution, you can think of having a set of empty covers for intuition. Each cover runs its own copy of the single cover method separately. The method takes a load vector estimate v prime as input for the future load it expects to see. Then when an interval I arrives, it needs to decide whether to accept it to the cover or reject it. Each cover accepts an interval only if it needs it to achieve a target lower bound. In the uniform case, you can think of each cover trying to get at least load 1 at each time. The cover will reject an interval unless it realizes that the rejection will not leave enough future load for it to reach its lower bound, in which case it will accept it. What changes between different covers is that the future load they expect and the intervals that they see. Okay, in other words, what changes between the different covers is the future load they expect and the intervals that they will see, which they can accept or reject. These parameters are controlled by the main algorithm. So not every cover will see the same intervals. In fact, covers that cover 1 has the option to accept or reject, and if it rejects an interval, it will move to cover 2. If cover 2 rejects, it will move to cover 3, and so forth. We'll see that in a second. Let's see now how it works using, let's show the algorithm through an example, and it's exactly the same kind of example that I've shown before. So as I mentioned, the future load for the instance, we know exactly what will be the future load going into the future is available to the main algorithm. So the first interval arrives. The main algorithm first gives an opportunity to cover 1 to decide if it wants to keep it. Cover 1 also sees the whole future load. It looks at how much load it should still expect and whether the interval is necessary. In this case, it turns out that the remaining load, if it rejects this interval, will drop to 1 at the time step that is kind of illustrated in the picture. So the load will drop below 1. So then the decision is, of course, to accept this interval. So it accepts it and makes it part of the cover. Now the second interval arrives at time 1, and a similar process is held, and the decision also, because if cover 1 does not accept this interval, its load will drop again below 1. So it asks the same question: do I need this interval to achieve my lower bound? And again, the answer is positive, and this interval is added to the cover. Okay. Things are different when the third interval arrives at time equals 2. Okay, the first cover looks at the first cover has a priority. It looks at this interval first. Now, between times 2 and 10, right, the lower bound of 1 has already been reached by the previous intervals. There is no incentive to receive more intervals. What happens between time 10 and 14, because this interval runs between 2 and 14, between times 10 and 14, the method sees that it expects to receive a lot more load. So no need to keep this interval now, because the load would not drop below 1 if we reject that interval. So cover 1 rejects the interval. Note that this procedure would not be possible if the method did not have information about the future load. So we need to have, in this case, the information about the load between times 10 and 14. As a small note, we don't need actually the total time horizon here. We just need to know, the information about the load until the end of that interval. At this point, the main algorithm gives cover 2 the opportunity to get this interval that was rejected by the cover 1. What changes here, though, is that the full future load is not revealed to cover 2. The main algorithm knows that cover 1 wants to keep load of at least 1. So what it shows to cover 2 is the future load of the entire system reduced by 1 at each time step. Right? Throughout the time horizon, we reduce the load by 1, and once we reduce this load by 1, then it turns out that this interval is actually needed by cover 2. So it accepts this interval, and proceeding similarly, cover 2 will accept also the fourth interval. The fifth, it is not either by cover 1 or cover 2, so it will be accepted cover 3. Cover 3, will not see the future load as is, but it will see the future load subtracted, decreased by 2, since the first 2 covers will have retained at least 2 units of load at each time. So here's an illustration of how we kind of assign the covers to the intervals to the different covers. All right. And this is the end result. We kind of assigned intervals to covers, and the theorem that we get by this process. So again, each cover uses 2 machines and schedules all the intervals that were accepted to it. The algorithm, then that's the main theorem here. The algorithm achieves a competitive ratio of 2 for the uniform case. Let me give you some intuition. Why is this the case? As we said, each cover is trying to create a 1-2 cover. If each cover knew the exact load it would receive, then it would successfully manage to do it. However, that's not the case, right? We said that cover 2 sees the future load as decreased by 1 because cover 1 wants to keep a load of at least 1 everywhere. But it might also keep load more than 1 at some point t. So cover 2 will expect to see some load at that time that will never arrive because cover 1 has already kept it. Okay, so decreasing by 1 is not precise, and due to that, so the V prime is actually an overestimate of the load that the cover will receive and can actually use. So for example, some intervals may not arrive, although the V prime indicated that the load would be higher. This overestimate parameter shows up in the guarantees for the lower bound. So instead of getting a 1-2 cover, we pay a little bit of penalty here in the form of delta t, right? So we might not be able to form exactly 1-2 cover in the uniform case, but it turns out that this is enough for our guarantees. In particular, we show a lower bound on the load the covers will accept, and more specifically, we show that the first J covers will accept at least a certain amount of load and at least a certain amount of J. So although maybe one of the covers went below 1, there is some kind of compensation if we kind of look at the aggregate of the first J covers, right? And this is used directly to obtain an upper bound on the number of copies required to accept all the load. So essentially, by this lemma, note that VT is an upper bound on the number of copies required to accept all load, right? This combined with the fact that we can easily schedule covers using 2 machines gives us directly the 2 competitive ratio result, right? Because we need basically we have VT covers. Each VT we have VT covers. Each cover requires at most 2 machines, and recall we have the lower bound that says that we cannot do better than VT. So here we have like the 2 competitive ratio quite immediately. So this is kind of the main result that proves the 2 competitive ratio. And again, it's a big improvement over the logarithmic factor that we've seen when we don't have this future demand information. But of course, I should admit that we are using more information, but you know, one has to know how to use that information, and this is what we show here. So that's the kind of the first algorithm when we know the entire load vector. I will just briefly explain what we do when we know only the average load on the system. Again, it's one number that we know, the average load of the system. This is actually in practice pretty plausible to assume that we have a very good estimate for this value. So let's now see that even with the knowledge of average load, we can design an algorithm that has better guarantees. Okay, so essentially it's opt plus order of like square root of opt t times log mu, an additive factor and not a multiplicative one. And just to mention the intuition, so with the essentially the covering algorithm, we packed horizontally. We found like intervals that pack that essentially we assign them to machines throughout time. So that's kind of horizontal packing. In the when we know only the average load, we cannot do that. So we have to kind of go vertically. And the intuition here is that, you know, if we have a high enough load at one point in time, we can probably find a set of intervals that can be nicely packed in at least one machine. What do we mean by nicely packed? That essentially all the intervals will kind of, you know, start at the same time, and also will occupy the node with good efficiency, maybe kind of cover the node almost entirely, so that there is almost no fragmentation. So that's kind of the intuition. And a little bit more about the algorithm, what we do in this case. The algorithm, instead of creating horizontal layers that cover the time horizon, groups intervals based on their length into classes. When an interval arrives, if the current load of the class is high, it scheduled it on dedicated machines with intervals from the same class only. And again, the intuition here is that if it's from the same class, they have similar duration, so they will also finish around the same time, okay? If the current class load is low, then it is scheduled on general purpose machines with intervals from any class. The intuition is that more compact scheduling can be achieved when intervals are similar in length and arrive closer together in time, okay? It is important to note that both the class limits and the threshold use the average load. So this is where we use the average load to essentially decide on the class boundaries, and also to decide what is considered as low load and what is considered high load for that particular class. This information allows us to create good classes and split the load well in order to achieve these bounds that we've shown in the previous slide. I won't go into, due to the interest of time, I won't go into questions here. Sorry, I won't go into details of the algorithm itself. I should just point out that you know, the algorithms, both in the low load case and the high load case, use kind of as building blocks, use pretty simple like combinatorial or straightforward like fitting algorithms, like the first fit and the next fit. However, the analysis, or how do we construct, how do we use these building blocks, is quite sophisticated, and that can be found in the paper itself. To conclude, we have seen two algorithms, each utilizing different kind of additional information on top of the VM lifetimes, future load vector or the average load. We see that even with basic information, like the single valued average load, we can improve performance of the scheduler. We have focused on the uniform case where all VMs have the same size. In the paper, we also generalize our results and obtain results for the non-uniform case where the VMs have different sizes, as I mentioned. But the principles are kind of the same. Another important thing to point out here is that our analysis assumed perfect predictions for the VM lifetimes and the different load information. Of course, it's a very strong assumption that doesn't hold in practice. Obviously, in practice, these predictions are prone to errors. Well, we do have some preliminary analysis in the paper of how we deal with errors or what's the impact of errors on our guarantees. But I should admit that still a lot remains to be done in that direction of embracing errors, and there's an active line of research essentially you can think of it as in the intersection of ML and algorithms, where in caching scenarios, memory management, in routing, we have some noise in some of the predictions of the quantity of the inputs, and how do we cope with that? And essentially we want to have some kind of consistency result that when the noise gets lower, we kind of converge nicely into the guarantees that we have without noise. So, just to conclude, we have like 8 minutes, and hopefully we can leave some more time for questions. Just kind of general thoughts that we have throughout our kind of work in this space. And first of all, I think that we have the cloud space, is fascinating, and there are many algorithmic problems and that kind of haven't been studied yet. So, for example, I would claim that in the OR literature, as much as I can follow, like the cloud is still kind of falls behind other domains such as healthcare, transportation, and others, although it's a huge business. So, but I do see some more interest in the OR community. Of course, in the EE community, the cloud is big. Folks like Shrikant and others have been working in this space for quite some time, Adam Weirman and others. So the problems are not only in the VM allocation space, but also in databases, network routing, data analytics, scheduling, and so forth. The expertise that we kind of need to solve these problems, I would say some kind of combination of OR and, okay, I wrote CS, but I meant by that engineering, CS, EE. So I think that that's because some of the problems, for example, if one wants to contribute to the actual allocator of VMs, let's say in Azure, you need to kind of understand the underlying system, some of like latency requirements, how a distributed system works, consistency, caching, and other things that come in play. And of course, there are some practical constraints that have to be accounted for. And that's what I mentioned. So oftentimes, the actual system is definitely much more complicated than the model that I presented today abstracts away other complexities, other combinatorial constraints, such as fault domains and so forth. So one of the things that we like to do in the group is, we start from like what we call a theoretical algorithm, a fundamental algorithm, and we have to translate it somehow, apply the principles, and translate it into a practical algorithm. Another aspect that I think I kind of hinted on is the combination between ML and optimization, which I think is key here in many of these problems, and that relates to Varun's question. We have huge amounts of data, so instead of kind of going online and solving like agnostically, not thinking about what data we saw, how can we utilize these huge amounts of data and towards better algorithms, more informed algorithms? And of course, this is an active area of research, both in the theory communities like Stock, Fox, Soda, but also, of course, in the more practical kind of disciplines. We see tons of ML for systems papers, but I think that the combination ML optimization, how do you incorporate these predictions into algorithms that utilize structure of the problem? I think that's, because here, for example, we have structure. We don't want to use just kind of a random ML model to decide how to schedule. We want to sort of exploit the structure, but bring ML as some sort of predictions on top to improve the performance. More generally, I would say that the cloud supply chain, which I discussed in the beginning, we do have there a lot of uncovered territory, and essentially maybe because traditionally some of these processes, for example, how do you do decommissioning of servers, have been done manually. And in the process of automation, you're also thinking, if I'm already automating and using software, why not optimize what we are doing? And again, each optimization here can result in hundreds of millions of dollars, if not more. One other area to think of, all that I've shown today, essentially, we are kind of thinking about how we improve, the costs and efficiencies within, let's say, the data centers of a cloud provider such as Microsoft, Amazon, and so forth. One interesting question that we are kind of thinking of, but we haven't done much yet, is how do we take some of the principles and actually, develop optimization solutions that apply not only internally, but can also serve other customers, for example, that have their own clusters and all that on-premise. How can they utilize some of this sort of solutions more like as a cloud service or a cloud application? So that's also an interesting area. And I should mention that we are, of course, hiring. So right now we are hiring an engineer, again, with this kind of combination of systems and algorithms. So if you know someone or if you're interested, please reach out. With that, I think we have 3 minutes, so a few more, I don't know. Yeah, thank you.
It was a very nice talk. There's at least one question from Wayna Wang at CMU.
Hi, how are you?
Could you share the reasons for picking the load vector / average load vector as the future information? Is it because that's the information you actually get from the machine learning algorithms and data, or is it because it's informative from a theoretical perspective? I guess the question is, did you make the assumption to make the theory easy, or is it that's actually what you have?
I would say, okay, the average load is, as I mentioned, I think it's very plausible to assume that that the average load of the system. You just need one number. I think how much can you be off? I mean, especially at large scale. Shrika, you know all the probability around that. So you can be off by a tiny bit. With the future load, I think yes, we do have aggregates. We do make these projections, for example, to make purchasing decision into the future. But of course, here you need a little bit more higher accuracy, I think. And I would say, you can definitely study this model that we have here and make some assumptions about the model itself or how noisy it is, and still try to obtain reasonable, more like going in the direction of robust algorithms and all that. So I do think that we make this I know that we make these projections into the future. So these are quantities that we have to predict, because we have to do capacity planning into the future at different kind of timescales. So definitely these are not arbitrary kind of quantities that we kind of put in order to get results and get a paper. So these are reasonable things that we do estimate, but with the caveat, of course, that here in this paper we are assuming that we predict with no errors, which of course it's a little bit of a strong assumption, especially when you look at the VM lifetimes. I would argue, because the VM lifetime, which is kind of, you assume that in dynamic beam packing, that's the assumption. The lifetime of the VM or of the interval. That's a very strong assumption, because here it's like you have to predict a quantity of a single VM of a single user. That's much harder, of course, than an aggregated predicting aggregate. So I think actually there, I think noise models definitely have to include also the errors in VM lifetimes.
I think we're at the top of the hour, so maybe we should stop here, since I guess people probably have other meetings. Thank you so much, Ishai. And
thank you.
If anybody has any questions for Ishai, please do contact him.
Yeah, Ishai@microsoft.com. It's easy. So
thank you so much, Ishai. Thank you for
okay. Thanks everyone for coming.
Bye.
Bye-bye.